Okay, welcome to POE. This is notes for day 32, Introduction to Structural Member Properties. This is going to be the first of a two-part series. The first thing we're talking about here is moment of inertia. This is a mathematical property of a cross-section measured in inches to the fourth that gives important information about how the cross-sectional area is distributed about a centroidal axis. Stiffness of an object related to its shape. In general, a higher moment of inertia produces a greater resistance to deformation. And what we're talking about here then is which way do we want this? Which one of these two ways that we have this, which way do we want to lay this plank to get the most stiffness? And there's a reason why they lay joists like this in, or the reason they lay a piece 2x4 or 2x6 or a 2x8 as a joist as opposed to a plank when they're trying to create support. Well, what distinguishes beam A from beam B? Well, as you can see here, obviously beam A is laid up on its edge and beam B is laying down on its face. Will beam A or beam B have the greater resistance to bending, resulting in the least amount of deformation if an identical load is applied to both beams at the same location? Well, I think all of us right now know that A is going to bend a whole lot less, but let's look at the math behind it. All right, why did beam B have a greater deformation than beam A? Well, if you look at our equation right here, the absolute main reason is the number one indicator in deformation is what's the height of the object. All right, because it's cubed. Everything else, the base is just to the first, but the height is cubed. So that makes it 3 times as important when it comes to this equation. All right, it is the number one indicator. The more height you have, the less deformation you're going to have. Okay, so having said that then, let's calculate the beam A's moment of inertia. Well, okay, what I've done here is I've identified that the base is the 1 1/2 inches and the height is the 5 1/2 inches cubed. So when it comes down to calculating this moment of inertia, we can say that inertia is equal to 1.5 times the 5.5 cubed, and it's going to be over the 12. The inertia then is 249.56, and it's going to be over 12. And when we divide that by 12, we get 20.79, which you can see that they've rounded to 21 inches. Now, what I want you to do here is I want you to go ahead and pause it, and I want you to calculate the moment of inertia. And when we get back, take a pause. I'm going to wait about 10 seconds here once I stop talking, and then I'm going to have the answer posted up on there for you to take a look at. But before I go, I want to make sure I point out here to you that this is the base. Even though it's on top, it's still the base, and our height is right there. So go ahead and work this out now. Okay, as you can see here, the inertia, 5.5 it goes in for the base, 1.5 goes in for the height, and then we have, if you multiply that across, you get 18.56, and on the bottom you're going to get divided by 12. That gives us 1.5 inches to the fourth, because this was, and I didn't talk about this last time, that was inches to the first. This is inches cubed. When you multiply that, you're going to get inches to the fourth. So even though we have the exact same numbers, putting them into different places into the equation obviously makes a huge difference as to why we have more a moment of inertia in one case than the other. So as you can see, laying the 2x4, in this case the 2x6, on its side, on its edge, gives us about probably, I don't know, 15, 16 times more, probably closer to 15, 14 times more inertia than what it does laying it on its face. Alright, and that's what I think they're going to, 14 times more is what they wanted to show here. You get 14 times more inertia putting it on its edge. Well, moment of inertia, composite shapes. Why are composite shapes used in structural design? Why don't they just use a big block of cement or a big block of metal? Why do they cut it into an L or a C or an I or this or hollow out the middle? Why don't they just use a big block of iron like that? Because it's not only the height, they also do want the base. Well, here's an example of where they've went ahead and did some um, calculated some moments of inertia for you. And at first glance, you're going to look at this and say, yes, all right, this makes sense. Why don't they just use a big solid piece of steel? You're going to get more moment of inertia. This right here is greater. 10.67 is much greater than 6.08. But let's come down to the area, because the area really comes down to how much steel's in it, which then relates to the price. If they give you a solid block of steel, the area becomes 8 inches squared, which means there's a lot of steel there. But over here, if they give an I-beam, I want you to notice what happens to the area. They get 3 times as much, almost 3 times, probably closer to 2 times. Let's change that to a 2. They get over 2 times the moment of inertia using an I-beam. Over here, do they get 2 times for every bit of area they have? No, they don't. And again, this just isn't cost effective. Why would you want to pay for all this extra steel here? All this extra steel if you're not getting the same bang for your buck. And that's why we have I-beams as opposed to these solid pieces of steel. Again, over here you're going to get over 2 times the moment of inertia for the amount of steel you have in it. And over here, when you fill it in, you're not going to get 2 times that. All right, so it comes down to the money. You'll hear me say that quite often. We talk about it's not about the money, but it's all about the money. Well, hey, I hope this was informational. I hope you enjoyed it, and I'll see you on the flip side.